Okay, so here we go with 8.2, graphing f of x equals ax squared, and then the new part is plus c. So just adding a plus c. In 8.1, we already graphed f of x equals ax squared. Okay, so go ahead and, again, same thing here. Try to do these on your own, and then pause the video, do them, and then come back and watch me uncover and go over it. Okay, so go ahead and try the warm-up. So here we go. So find the x and y intercepts. Remember, to find the y-intercept, we set x equal to 0. And to find the x-intercept, we set y equal to 0. So both of those are 4. In this case, the y-intercept is negative 11. Notice this is in y equals mx plus b form. And the x-intercept, what do we have to do? We have to set y equal to 0. And in that case, x would be 11. Okay. And then here, again, slope-intercept form. So we know the y-intercept is negative 13. And to figure out the x-intercept, we set y equal to 0. We would add 13 to both sides, divide by 2, and get 6.5, or 13 over 2. Okay, complete the statement with always, sometimes, or never. Explain your reasoning. If x squared equals y squared, then x is sometimes equal to the absolute value of y. Why would that be, or the reason for that, excuse me. So think about it. If x could be the opposite of y, right? And in that case, it would be different than the absolute value of y. Okay, number 2, if x and y are real numbers, then the absolute value of x plus y is blank equal to y plus x. That would be always. It wouldn't make a difference, right? If you add numbers in different orders, it doesn't make a difference. Okay. Moving on. Okay, our learning target will be to understand how the value of c affects the graph of f of x equals ax squared plus c. And really not a huge step from what we did before, so which is nice. Okay, so obviously you're not going to work with a partner here. We're going to sketch the graphs of the functions in the same coordinate plane. So here we're going to do f of x equals x squared, our parent function. And then we're going to do g of x equals x squared plus 2. So for f of x, I've given you the numbers that we're going to plug in for x. So go ahead and do each of these. I would use maybe a different color for the g of x one than the f of x when you graph, just to make it easier for you to see. Okay, go ahead and try it and then come back. Okay, so obviously for f of x, if x is 0, f of x is 0, and 1, and these will be 4. And for g of x, if we'd have 2, right? Because if this becomes 0, then plus 2, plus or minus 1, it's going to be 1, or negative 1 squared is 1, plus 2 is 3, excuse me. And if I plug in 2, it's going to be 4 plus 2, which is 6. So when you go and graph these, we have, right here, we have f of x equals x squared. And here for g of x, everything is what? It's just kind of like shifted up by 2 units, isn't it? Okay. And go ahead and try this one on the right. Here we have 2x squared, and here it's 2x squared minus 2. I bet if you think about it, you will know what the g of x one looks like compared to the f of x before you even start. So go ahead and try that. Okay, and so if you hopefully got 0, 2, and 8 for that, and for g of x, negative 2, 0, and 6. And notice how for the same x value, the y value is shifted down by 2 units, right? So when we go and graph these, here's our f of x in red, and in blue we have our g of x. Everything is shifted down too. So notice that this is 2 lower. If I take the same x value, you can see that it would be from there down to there. That's 2 units. So it's 2 units all the way along. Okay, so it should be telling you how c is affecting things. But let's get into trying a few more of these. So let's graph x squared minus 7. And we're going to need to find the x-intercepts of the graph. Okay, and you need to explain how you're going to find the x-intercepts. Think about what an x-intercept is and what's true of every x-intercept. Okay, so here's the numbers to plug in, 0, plus or minus 1, plus or minus 2. Go ahead and try it. Okay, well hopefully you got -7, -6, and -3, because if you plug in plus or minus 2, either way that becomes 4, -7 is -3. And when you graph that, it should have looked something like that. And what would the x-intercepts be? Oh gosh, it's hard to tell just from looking at the graph. So what would you need to do? Well, you need to set y equals to 0, right? So that would mean that x squared equals 7, and that x equals plus or minus √7. Okay, because we could literally like take the square root of both sides, right? Okay. All right, so the x-intercept is approximately plus or minus 2.6, which is what it pretty much looks like on our graph. Okay, try y equals -x squared plus 1. And here's the numbers to plug in. Go ahead and try it. Okay, I'm back. Hopefully you got 1, 0, and -3. And then you plotted those 5 points, drew your curve in as best you could. And it should have opened downward and looked like that. So, well, interesting. When y is 0, we know that x is plus or minus 1. Aren't those going to be our x-intercepts? So you could do it this way, but we also kind of have the information from the numbers that we picked. But if we ended up doing it the same way as we did over here, yes, we could set y equal to 0, and that will equal -x squared plus 1. We'd subtract 1 from both sides, divide by -1. So we'd have 1 is equal to x squared. We could take the square root of both sides, or just think about it. What squared is going to equal to 1? 1 and -1. So our x-intercepts equal plus or minus the square root of 1, which is plus or minus 1. Okay. So here's the actual kind of core concept that we're getting into when we're graphing f of x equals ax squared plus c. Okay. When c is greater than 0, what did we see in the problems that we did? Well, we would have ax squared plus c in green, right? It's a vertical translation, c units up. So if c was like 3 here, then that means we would be at 0, 3 right here for our vertex. Okay, so you can see we're not talking about changing whether it's stretched or shrunk or more bowl-shaped or anything like that. We're just moving the same parabola up. Okay, and if c is less than 0, then we would be shifted down or translated down that c number of units. So if c was -2 right here, then this whole blue parabola would just be pushed down 2. Okay. So the vertex of the graph would obviously be 0, c, right? Because, like I said, if c was 3 here, it would be 0, 3. And down here I said I think that c was -2, it would be -2. And the axis of symmetry is still the y-axis, or x equals 0. Okay. So let's try graphing this one and then comparing it to your parent function, f of x equals x squared. So think about what it should be. I've given you the numbers to plug in. So go ahead and plug those in, give it a shot, and come back. Okay. Hopefully you had -2, -1, and 2. Graph those 5 points. Draw your curve as carefully as you can. And you should have gotten what's in black here. The green was our parent function. I should really make this green, shouldn't I? Let's see if I can do that. All right, let's make that green. There we go. Okay, so what would you do? What would you say? That it's what? Vertically translated down 2 units. Vertical meaning up and down, and it's down 2 units. Okay, try this one. Again, I've given you numbers to plug in. Go for it. Okay, hopefully you've got 3, 4, and 7. So we have 5 points to plot. Go ahead and graph them. And our parent function here again is in green. And what you graphed would have been up here in black. And how would you describe this? That it's a vertical translation 3 units up. Okay, let's go on. Okay, let's try 4x squared plus 1. So now we've got a leading coefficient that's not the same as our parent function. So think about what that's going to do to the graph. And then we have a c here of plus 1. All right, so those are your numbers to plug in. I'm using plus or minus 1.5. So you can use that as 3 over 2, which is easy to do. Or I guess you could use a calculator and use 1.5. Okay, so hopefully you got 1, 5, and 10. Graph those 5 points. And your parent function is obviously in green. What you just graphed is in black. And what do you notice? It's definitely steeper, right? So it's a vertical stretch. And the graph is vertically translated 1 unit up. Okay, so it's steeper, it's vertical stretch. Think about like stretching your arms up, and the whole thing is moved up by 1 unit. Okay, so 2x squared minus 5. Think about what you think this one's going to look like. Is it a vertical stretch or shrink? Is it going to be translated up or down? And then go ahead and plot these points. So -5, -3, and 3 would be the g of x or the y coordinates for those x coordinates. Plot the 5 points. And you should have gotten what's in black. Green is our parent function. How would you describe it? It's definitely a vertical stretch, steeper, right? And it's translated down by 5 units. Okay. What about this one? -1/4 x squared plus 4. Try it. Okay, so we would have gotten 4, 3.75, and 3. Wow, this one's going to be pretty shallow, isn't it? Okay, so we graph that. You should have had what's in black. Okay. So how does that compare? Well, it opens downward instead of upward. And it's what? It's translated 5 up. So it's a reflection, right? So it's downward instead of upward. It's a vertically translated 4 units up. Look at where the vertex is here and where the vertex is here. And it's a wider graph, so it's what we call a vertical shrink. It's more bowl-shaped. Okay. All right, moving on. Okay, so we have let f of x equal -0.5x squared plus 2, g of x equals f of x minus 7. Okay, so basically g of x is the same as f of x except minus 7. Think about what that would do with g of x compared to f of x. Okay, so then A, write an equation that represents g in terms of x. So in other words, what we need to do is plug in f of x, -0.5x squared plus 2, right here. So we have -0.5x squared plus 2, and then the minus 7. What does that simplify to? -0.5x squared minus 5. Okay, so what do you think the transformation from the graph of f to the graph of g will look like? Well, hopefully you think it will be a vertical translation 7 units down. Okay, so notice instead of c on f of x being plus 2, for g of x it's now -5. Isn't that 7 units lower? Okay, so then let's go ahead and graph both f of x and g of x. So f of x is right here. G of x, we're going to use this function right here and graph those. Go try it. Okay, for f of x, you should have had 2, 1.5, and 0. For g of x, again, we're plugging in right here. You should have had -5, -5.5, and -7. Let's look at one of those. Like if I plug 2 in, 2 squared is 4. 4 times negative 1/2 or negative 0.5 is negative 2. Negative 2 minus 5 is negative 7. Graph both of those. And again, that'll take you some time, but that you can pause the video. And you should have gotten this. Okay, so this is f of x. This is g of x. And what would you do if we didn't ask you to describe them, but basically we translated 7 units down. And is it a stretch or shrink? No, it's still the same negative 0.5 leading coefficient on both of them. Okay, so here's the same type of problem. So go ahead and try this one. Okay, I'm back. So we're writing an equation that represents g in terms of x. We're basically just going to plug 3x squared minus 1 in for f of x. Combine your like terms, the negative 1 and the 3, and you get 3x squared plus 2. So what do you think it's going to look like, g of x compared to f of x? Well, hopefully you see that it's going to be a vertical translation 5 units up, right? We're going from negative 1 for our c in f of x to a positive 2c in g of x. Okay, and then go ahead and graph them. So it had negative 1, 2, and 11 for f of x. And when you plug in for g of x, you have 2, 5, and 8 3/4. I know that's tough to graph. You could have used something else, but just do your best. Remember, that's 5 points for each of these, so you should have 10 points on your graph and then 2 curves. And when you do, you should have gotten something that looked like that. Again, it's not a stretch or a shrink because our leading coefficient 3 is still the same. Our a is 3, but our c is off by 3, which is why we have one that's translated, g of x is translated like that. Okay. A zero of a function, f, is an x value for which f of x equals 0. A zero of a function is an x-intercept of the graph of the function. Okay, so a zero function is just another way of saying the x-intercept, okay? Means the same thing, just another term that we use for it. Okay, so the function f of t equals negative 16t squared plus s sub 0 represents the approximate height in feet of a falling object t seconds after it is dropped from initial height of s sub 0, and that's in feet. Okay, and we've seen these before. We've seen problems where we've had like negative 16t squared, plus 16 or something like that. We saw that, I think, with the water balloon problem. Anyway, okay, so we have an egg that's dropped from a height of 64 feet. So graph the function to determine how many seconds it takes the egg to hit the ground. Well, what would be our function for that if we know that the initial height is 64 feet, because that's what the egg's being dropped from? Well, we plug in 64 for s sub 0 and have f of t equals negative 16 squared plus 64. Okay, and then you need to graph it. Notice here I've labeled my axes, f of t and t, or time in seconds, right? And this is our height. So at 0 seconds, isn't that like right when I start to drop it? So if we plug in 0 for this, what's our height going to be? It's going to be 64. Okay, after 1 second, the egg starts to fall, right? 1 squared is 1, so it's negative 16 plus 64 is 48. At 2 seconds, it's fallen even further, right? 2 squared is 4 times negative 16 is, negative 64 plus 64 gets us 0. Okay. So if we graph this, it would look like this, okay? And why do I not have this part of the graph over here? Because this is a real-life problem, right? The egg's not being thrown up and then coming down. It's just being dropped, okay? If we graphed this function, yes, if we graph the whole function, it would be a parabola just like we've seen all along, and it would continue on forever. But that's not the case in this real-life situation. Okay, part B says, suppose the initial height is adjusted by k feet. Okay, so we're saying we would change 64 by a certain amount called k. How will this affect part A? Well, what do you think? Well, if k was greater than 0, then it would be take longer because that means 64 would be, k would be added to 64. It would become a bigger number, right? If k was 10, then this would become 74. That means it would be higher and then obviously take longer for it to fall to a height of 0. And if k was less than 0, let's say k was negative 10, if I combine that with 64, then I would be dropping it from 54, and that would take less time. Okay. Okay. Again, I already went over this, but explain why only non-negative values of t are used. Because it's a real-life situation. Can you have negative time? No. Okay. What if? What if the egg is dropped from a height of 100 feet? After how many seconds does the egg hit the ground? How can you figure this out without graphing? Well, if you want to know when the egg hits the ground, doesn't that mean you want your height to be 0, right? So you would set your h of t equal to 0. And then we would need to solve this using factoring if we weren't graphing it. So what would we do? Well, you could factor out GCF of -4. Notice we have what here? A difference of 2 squares, don't we? 2t times 2t is 4t squared, and 5 times 5 is 25. So we could factor that further. It's fully factored now. It's set equal to 0. It's in factored form. So we can set each factor equal to 0. And obviously -4 equals 0 is gibberish. Get rid of that. And solve these, and we get plus or minus 2.5. Well, which one are we going to use? The positive one, obviously, because we're dropping it, and then we're going to go to positive time. Can't have a negative time. So it would be 2.5 seconds. Okay, so I think that does it. It does for 8.2. Hope you enjoyed it, and I'll take questions on it our next class, and then we will try the homeworks on those. All right, talk to you later. See you soon. Bye.